Hey y'all, it's your personal math teacher, Mr. Boyden, back at it again, finishing up our probability unit today. And today we're going to continue our discussion of conditional probability, which we've talked about in the last two, but we're going to see some more conditional probability. I'm including that because I know sometimes that can be a confusing topic. So we're visit that again today, and we're also going to talk about independence. Okay, let's start right away with independence. So two events are considered to be independent events if the occurrence of one does not change the probability of the occurrence of another. Okay, and so here we have just a really simple example. If we flip a coin and get heads, what is the probability that our next toss is heads? Okay, so the probability of getting heads the first time was 1/2, and the probability of the second time is whatever you got on the first one. It has nothing to do with the second one. That's what we mean by independent. Like knowing what you got the first time doesn't change the second one, so that's also a 1/2. Sometimes this can trick people. So like if I flip a coin and I get heads 10 times in a row, what's the probability of getting heads on the next throw? It's still 1/2. I mean, unless the coin is rigged or something, I guess that could technically happen. But assuming it's a fair coin, the probability doesn't change. Sometimes weird events like that are going to happen. It just freak things happen, but that probability doesn't change. This actually leads to something called the gambler's fallacy. That like you get hot and you get cold with luck, and or like if you've been playing a game and you've lost 10 times in a row, you say, oh, people will say I'm due to win, or like I've lost so much, I'm gonna win soon. Well, you're no more likely to win now than when you started, and you just so happen to have lost a bunch. Or people say the same thing if they're rolling dice or something and they're doing really well. They say, oh yeah, I'm on a hot streak, I keep winning. Well, your next roll has nothing to do with the ones that just happen. I mean, they're dice. Your dice don't have memory. They're not that smart. So they don't know that it's their turn to land a certain way or not to. Okay, so those are independent events, and sometimes it seems so simple when I explain it like that, probably, but there is a logical fallacy with independent events that we can fall into. So be careful. All right. Now, there's a couple of things that I wanted to help you understand today. And what I did is I put all of them into one big question. And so we're going to do one big question and we're going to do one small question. And that's actually today's whole lesson. Okay. And so here is the big question. A computer company, or let me shrink this down and zoom in so we can see it better. A computer company makes desktop, laptop, and tablet computers at factories in California and in Texas. Oh man, that's already a lot of information. The California factory produces 40% of the company's computers, and the Texas factory makes the rest. At the California plant, 25% of the production is desktops, 30% is laptops, and the rest are tablets. In Texas, it's 10% desktops, 20% laptops, and the rest of them are tablets. Now, guys, I do want to say this question is a couple years old, and I know that we would normally not call tablets computers, but this question is calling tablets computers. So just so you know, like, don't get thrown off by the word computer. They're calling those computers. Okay. When the computers are assembled, all of them are sent to a shipping depot in Missouri before being sent to the stores. If we select a computer at random from the shipping depot, we have some questions to answer about that. Now, did that feel like a lot of information as I was reading that? It sure felt like a lot to me, and I'm already confused by it. So that's why prompt number 1 is we need to make a model of this chance process. Now, because you already know that in about 15 seconds I'm going to show you what it is, but I do want to give you a chance to pause the video and try to figure out a way of organizing this information. Now, there's more than one right way. There is a way that most teachers will do and that I like as well. It's my favorite way to do it. So I'm going to do that now. So pause if you're not ready for that. Okay, what I'm going to do is I'm going to make a tree diagram. And how do I want to do that? So I'm just going to kind of think through the information as we start. They tell us that California makes 40% of the company's computers and the Texas factory makes the rest. So I'm just going to come down here and I'm just going to write CAL for California and TEX for Tex. And they told us California produces 40%, so 0.4 of the computers are made in California, and the Texas factory makes the rest. That's a complementary probability, so 0.6. Notice those two numbers add up to 1. That's 100% of the computer production. At the California plant, 25% is desktop, so I'm going to put a D for desktop, 0.25. And at the California plant, 30% is laptops, so 0.3 is laptops, and it says the rest are tablets. Now, do I know that third probability? Yeah, I do, because they make desktops, laptops, and tablets. And I have 25% and 30% already taken up. So what do I have left over? So 25 plus 35 is, plus 30, excuse me. Plus 30 is 55, which means that there's 45% left over to make tablets. Let's keep reading. In Texas, 10% are desktops. So we're going to continue with this tree. The desktops are 10%, and 20% are laptops. So the laptops are 0.2, and tablets are the rest. And if you have 30% there, there must be 70% tablets. So that's the model. That encompasses all the information. And then at the end, they send them all to Missouri. But this is the model of the process. Now, let's see if that helps us to answer the probability questions below. Find the probability that a computer is a tablet. So if you select a random computer, so what's the probability that it's a tablet? Well, where are my tablets at? I got tablets here. And so I may have selected a California tablet if I picked one, or I might select a Texas tablet. So we need to find those probabilities. So this is where I want to remind you. The way you find the probability of selecting a tablet from California is you just multiply along the branches that get to that location. And so what that would look like is 0.4 times 0.45. And so if you randomly select one item, there is an 18% or a 0.18 probability. I'm going to go 0.18 so you can see the point better. That's the probability of getting a tablet from California. Now let's repeat that process for a Texas tablet. So 0.6 times 0.7. And that is 0.42. So that's our Texas tablet. So the probability of getting a computer that's a tablet, it's 0.18 plus 0.42. So what this tells us is that 60% of the computer production at this place is tablets. Now, this question's a couple years old, and I mean, tablets are still cool, but tablets were all the rage, and people were buying them a lot more than they were buying computers back then. So that would make perfect sense. All right, so guys, that's number 2. Now let's go to 3. Given that a tablet is selected, okay, when they say given like that, that's hinting that it's conditional probability. It's a given that a tablet is selected, so we're only going to be thinking about tablets. We're no longer thinking about desktops and laptops now. What is the probability that it was made in California? So let's start here. Where are our California tablets? My California tablets are right there. So this is 0.18, but it's conditional. So guys, normally probability is out of 1. This one is not out of 1. This right here, they're trying to tell me the denominator. Okay, so the denominator is the probability of selecting a tablet. We already know that because that was the answer to question 2. So this is 0.18 out of 0.6. And that is 0.3. Or another way to interpret that is that 30% of their tablets are made in California, and of course then 70% of the tablets are made in Texas. Okay, so this is a way of reducing down a really, really big, complicated problem into something that's simple. This is why I'm such a big fan of tree diagrams. Any chance I have an opportunity to use a tree diagram and it's helpful, I'm going to do it every time because it just lays out all the information, and then it helps me realize what's extraneous information and what's not, because some of the information here was kind of extra. Although we needed these two to find that one, for example, but in any event, at least this helped us to organize it. Let's do one more example. Okay, and this one's a little bit different. So here it is. At SeaTac Airport, 93% of all flights arrive on time. If we randomly select 10 flights, what is the probability that all of the flights are late? And what is the probability that at least one of the flights is late? Okay, so how would we think about that? The probability that all of the flights are late. So what chain of events would have to transpire in order to meet the criteria for A? So you would have to have a flight be late. So what is the probability that the first flight is late? That probability, well, if on time is 93%, the probability of being late would be 0.07. So that's the first flight being late. And then the next flight would have to be late. So that one also, because they're independent, that's a 0.07. And so on. And that would happen 10 times. Or we could write that a different way as 0.07 And since there's 10 flights, that would be to the 10th power. Now that's not going to be much of a number at all, y'all. I mean, that's going to be a really small number. Wow, it's a number preceded by 11, like point and then 11 zeros. So I'm going to say that's basically 0. Could it happen? Yes, but it's basically not going to happen if you truly randomly select 10 flights. That's basically none. Okay, so that's the setup. And really what's important is understanding how to do the setup. Now, what is the probability that at least one of the flights is late? It might sound like a similar question, but until you know the trick to it, this question's way, way, way harder. Because when we say at least one of the flights is late, what are all the different things that could happen? We could have one flight late, or you could have 2 flights late, and so on, all the way down to 10 flights late. And yet it gets even worse than that, because if you have 1 flight late, it could be the first flight that's late, or the second flight that's late. You don't know which one it is. So there's so many different ways that at least 1 flight could be late. So when you get into a situation like this that's really hard to think about, a better way to think about it is the complement. So what is the opposite of 1 flight, of at least 1 flight being late? Because that was 1, 2, 3, all the way up to 10. The opposite of that would be, the complement, I should call it, is no flights being late. So how would we write that? The probability of at least 1 flight being late is the same as 1 minus the probability of no flights being late. Because those are opposites. Those two things, they're complements. Those two things would have to add up to 1, and so if you do 1 minus one of them, you get the other. And that turns out to be a much easier question, because you go 1 minus, you think about, no flights being late. No flights being late means all flights being on time. So the first flight would have to be on time. That has a known probability of 0.93. And then the next one, and the next one, and the next one, and the next one. The rest of them would have to all be on time. So that's to the 10th power. So, calculator time. And I'm just typing that in, and I get 51.6. They asked for a probability, so I'm going to write it as 0.516. Okay, and so let's think about it. You do know that most of the flights are going to be on time, because 93% of them arrive on time, but that's not 100%. So if you pick 10 flights, about half the time, all 10 of those will be on time, is what that's saying. And that kind of makes sense if you think about it. So the purpose of part B of this question is to show you another way of thinking about probability. So, because sometimes you're going to get a situation where you are like, oh my gosh, there's so many different ways that could happen. How would I ever calculate all of them? That's really, really hard. It's much easier to think about the flip side of that, so to speak, or the complement. So at least 1 flight being late, the opposite of that would be if none of them were. And so that's a much easier thing to calculate. All right, y'all, today's a short one. That's going to be it. I hope you enjoyed it, and I'll see you next time.